Today we're going to continue with simplifying radical expressions. This time we're talking about when you have dividing underneath a radical sign. First off, no radical in the denominator. So when you're simplifying, to be simplified, you cannot have a radical in the denominator. So if you do, you're not done yet. You're going to do what's called rationalizing the denominator, which we'll talk about here in just a minute. So if you have the square root of a over the square root of b, that's equivalent to the square root of a over the square root of b. So in number 1, we can break this down into the square root of 49 over the square root of 4. Square root of 49 is 7, square root of 4 is 2, and then we're done. So that's a pretty easy one. Now in this case, neither one are perfect squares, so we don't want the square root of 3 in the denominator. So we're going to do what's called rationalizing. I'm going to multiply by 1 is really what I'm going to multiply by, which does not change the value, but how can I get rid of a square root of 3? Well, I need to multiply by the square root of 3. So if I do that on the bottom, I really need to multiply by the square root of 3 over the square root of 3, which is the same as 1. So on top, I'm going to get the square root of 30. On the bottom, the square root of 3 times the square root of 3 would be either the square root of 3 squared or the square root of 9. Usually you don't even have to write this step out. So that gives you the square root of 30 over 3. Now you do need to look to see if there are any perfect squares in 30, because if there are, you will have to simplify farther, and in this case there are not. So this would be my answer. But remember, you have to always simplify. Never leave a perfect square underneath the radical. So that's why you got to become familiar with those factors and perfect squares. In some problems there are different ways to do it, so I'm going to show you 2 different ways to do this problem. You might recognize that 8 would be the square root of 4 times 2. So it's the same as the square root of 7x over 2 times the square root of 2, because I simplified there. Actually, my radical's over the whole thing. Now, all I need to get rid of then is the square root of 2. I can have a whole number 2 on the bottom, so I'm going to multiply by the square root of 2 over the square root of 2 to rationalize my denominator. So I can multiply the things when they're underneath the radical, so that's going to give me here the square root of 14x. And on the bottom, I'm going to have 2 times the square root of 4, which would be square root of 14x, and then the square root of 4 is 2. Bring it out and multiply it by the 2 I already have. I'm going to end up with a 4. So the square root of 14x all over 4. Now, there is another way to do this. I think it is a little longer, but let's say you didn't recognize that there's a perfect square in 8. I'm not sure I'm going to have enough room to do this, so I'll write it and then maybe get rid of it. So let's say we have the square root of 7x over the square root of 8, and we chose to multiply by the square root of 8 over the square root of 8. So you're going to get the square root of 56 over 8. But then you should say, well, 56 has a perfect square in it, and it's not as, oops, lost my x there, and it's not as easy to see, so many of you might not know this, but this would break down into the square root of 4 times 14 times x all over 8. Square root of 4 is 2, so I'm going to go ahead and take that at the top. So 2 times the square root of 14x all over 8. And now I have to simplify these that are outside the radical to get the square root of 14x all over 4. So I am going to erase that in a minute so I have room to do my next problem, but that's another way. Now, is that way a little harder? Probably, I mean not harder, but longer. And you might not recognize the perfect square in 56. So it's probably easier to look at them in smaller numbers. So make sure you're looking for perfect squares. So let me erase that now, and then we'll go on to the next problem. So looking at the next problem, again, this one has 2 ways to do it. I'm going to do the longer way first because many of you might not recognize what I'm going to do the second time. So we want to rationalize, so we need to get rid of the square root of 6 on the bottom, so I'm going to multiply by the square root of 6 over the square root of 6, which gives me the square root of 12 over 6. Are there any perfect squares in 12? Yes. 12 breaks down into 4 times 3. Square root of 4 is 2, so 2 times the square root of 3 all over 6. And here we have to do what I just showed you about canceling. They're not underneath the radical, so we can cancel like that and get the square root of 3 over 3. So that would be my final answer. Now, I could, with the square root of 2 over the square root of 6, remember the first on the first slide we talked about the definition of that. That goes back to the square root of 2/6, which would reduce to the square root of 1/3, and then I can break it down into the square root of 1 over square root of 3, and then I can rationalize that and get the square root of 3 over 3. So that way is shorter if you notice that, so you can put them under one radical and simplify if that makes it easier for you. So there are a lot of little tricks to learn here of how to do this that makes it easier for you probably. And this last problem is more of a review of the other lesson. So are there any perfect squares in 75? Yes. 25 times 3. Are there any perfect squares in n to the 5th? Yes. M to the 4th times m, and then n to the 2nd. So taking my perfect squares, I get 5, m to the 2nd n, and what am I left with? 3m. So I would be done there with that one. And again, if maybe the absolute value, if you want to get in the habit of putting that, that's fine, but you don't have to. So that would be that one.